Welcome to our lecture on the Kolmogorov-Smirnov test. Imagine you are relying on a city bus schedule to get to work. The official schedule says buses arrive exactly every 10 minutes. But when you stand at the bus stop, the actual arrival times might be quite different. If we measure the largest gap between what we expect to happen and what actually happened, we can tell if the schedule is accurate. This is exactly what the Kolmogorov-Smirnov test does with statistical data. Now that we have our bus analogy, let us look at what this test actually is. The Kolmogorov-Smirnov test, or KS test, is a non-parametric statistical method. This simply means it does not assume our data follows a familiar bell curve or any strict shape beforehand. Instead of just looking at averages or variances, it looks at the entire shape of the data all at once. It checks if your real-world data matches a mathematical model by finding the single point where they disagree the most. If that maximum disagreement is too large, we reject the idea that the data fits the model. Before we can find that maximum disagreement, we need to build a curve from our actual data. We call this the empirical distribution function. The word empirical just means it is based on actual observation rather than pure theory. Think of this function as a step-by-step staircase. As we move through our sorted data points from smallest to largest, we take a step up every time we pass a data point. This staircase climbs from 0 to 1, giving us a perfect visual representation of how our actual data accumulates over time or space. Let us look at the mathematical formula for this empirical staircase. F hat of x represents the empirical distribution function at a specific value x. The symbol n is the total number of observations in our sample. The term I is an indicator function, which is just a mathematical switch. It equals 1 if the data point is less than or equal to x and 0 otherwise. In plain English, this formula tells us to count how many data points are smaller than or equal to x and then divide by the total number of points. As x increases, this fraction grows from 0 to 1. Now that we have our empirical staircase and our smooth theoretical curve, we need to compare them. The KS test statistic is simply the largest vertical distance between these two graphs. We look at every single point along the horizontal axis, measure the gap between the theoretical expectation and the actual data, and pick the absolute biggest gap. Because it looks at the maximum difference anywhere along the curve, it is highly sensitive to both the center and the spread of the data. Also, this statistic is distribution-free, meaning its cutoff values do not depend on the specific distribution we are testing against. This brings us to the formula for the test statistic itself. In this equation, D is the Kolmogorov-Smirnov test statistic, representing that maximum distance. The function f of x is the theoretical cumulative distribution function, which tells us the expected probability. The function f hat of x is our empirical distribution function, representing the actual observed probability. The vertical bars mean we take the absolute value, so we only care about the size of the gap, not the direction. If D is larger than a specific critical value, we conclude our data does not fit the theoretical model. Let us visualize this maximum gap. On this graph, the horizontal axis represents our data values, and the vertical axis represents the cumulative probability from 0 to 1. The smooth blue curve is our theoretical expectation, f of x. The red staircase is our empirical data, f hat of x. Notice how the staircase climbs up and follows the general shape of the blue curve. The black double-sided arrow labeled D shows the single point where the vertical distance between the red steps and the blue curve is the absolute largest. This specific distance is our test statistic. Before we calculate this ourselves, you should know the KS test comes in two main flavors. The one-sample test compares a single set of data against a specified, known mathematical distribution, like checking if test scores follow a perfect normal distribution. The two-sample test, on the other hand, compares two different sets of empirical data against each other to see if they come from the same underlying population. Instead of comparing a staircase to a smooth curve, the two-sample test compares one staircase to another staircase, looking for the maximum vertical gap between the two empirical lines. Let us see this with a concrete example of a one-sample test. We have a small sample of three numbers, 0.2, 0.5 and 0.9. We want to test if these come from a standard uniform distribution between 0 and 1. First, our data is already sorted. At our first point, 0.2, exactly 1/3 of our data is accounted for. So our empirical value is 0.333. For a standard uniform distribution, the theoretical probability is simply the value itself, which is 0.2. The absolute difference here is 0.133. Continuing with our next data points, at our second point, 0.5, 2 out of 3 points are accounted for. This gives an empirical value of 0.667. The theoretical value is exactly 0.5. Subtracting these gives a gap of 0.167, which is our largest gap so far. At our final point, 0.9, all data is accounted for, so the empirical value reaches a perfect 1.0. The theoretical value is 0.9. The absolute difference here is 0.1. Now we gather all the absolute differences we just calculated. We compare 0.133, 0.167 and 0.1 to find the absolute largest value. The maximum value among these is 0.167. This maximum gap becomes our official test statistic D. Because this maximum gap is relatively small, the empirical staircase stays very close to the theoretical line. We would likely conclude that the data does indeed follow a uniform distribution. Now let us look at a two-sample test. We have sample A with values 1 and 3 and sample B with values 2 and 4. We want to see if they come from the same population. First, we combine and sort all unique values to get a master list, 1, 2, 3 and 4. At the value 1, sample A has 1 out of 2 points, giving a probability of 0.5. Sample B has 0 points, giving 0. The absolute difference between these two empirical staircases at this first point is 0.5. Moving along our master list, at the value 2, sample A still only has 1 point, so it stays at 0.5. Sample B now has 1 point, so it rises to 0.5. The difference here completely closes to 0. At the value 3, sample A reaches its maximum with both points, giving 1.0. Sample B still only has 1 point, staying at 0.5. We subtract these and the gap opens up again to a size of 0.5. Finally, at the value 4, both samples have accounted for all their data points. Both empirical step functions reach their maximum height of 1.0. The distance between them here is 0. Reviewing all our vertical gaps, we have 0.5, 0, 0.5 and 0. The absolute largest number is 0.5. This is our two-sample test statistic. It tells us the maximum vertical distance between the two empirical step functions is half the total probability. So why do we go through all this effort? The Kolmogorov-Smirnov test is incredibly important because it does not force us to make blind assumptions about our data. Many powerful statistical tools like the t-test or ANOVA strictly require the data to follow a normal bell curve. If that assumption is wrong, the results are completely invalid. The KS test acts as a crucial gatekeeper, allowing researchers to verify the shape of their data first. It is widely used in fields like finance to check risk models, or in manufacturing to ensure parts match specifications. Let us summarize what we have learned. The Kolmogorov-Smirnov test evaluates how well data fits a distribution by finding the single largest gap between the observed data and the expected model. It relies on the empirical distribution function, which is a step-by-step accumulation of the data. By focusing on this maximum absolute difference, it provides a robust, distribution-free way to test assumptions without relying on averages or variances. You now have a fundamental tool for verifying data integrity.